Okay, 4.5, applying Pascal's method. So Pascal's triangle can be applied when counting paths and routes. So what we do is we begin at 1 at the starting position. And for example, if we have a grid like the one below here, we begin at 1, and it's almost like it's Pascal's triangle on its side. Okay, because this is going to mimic row 0, entry 0. Then when we branch down to the sides, we're also going to put a 1 and a 1. And what this would mean is there's only one route to go from this starting point to this point here. Let me get rid of that. And this starting point to get to this point here, again, only one way to travel. Okay. And moving toward the outside, we're going to continuously put, for these nodes, we're going to put 1s. Because there's only one way. I mean, if we're flowing from the top left corner to the bottom right corner, this is the end. This is the beginning, so start. There's only going to be one way if we're flowing down and to the right to get from this starting position to any one of these nodes, and then this starting position to any one of these nodes here. Okay, and when I say node, that just means these points. Okay, then what we're going to do is we're going to move toward the middle, and we're going to be adding these outside numbers with our original equation there. So we learned this in 4.4 section. Okay, and we're going to fill up the middle and eventually get to the end. So apply to a question. Example 1, counting the number of roots. How many roots are there to get from the corner of Pythagoras and Kovalansky Avenue, which is right here, and that would be the start, to the corner of Fibonacci and Euler? Okay, and if you guys know any mathematicians, these are definitely the last names of mathematicians. Okay, so by the way, I think it's Euler, not Euler, but I say Euler. Okay, so we put 1s on all the sides, and this is like if you rotate your paper like this way, you'll be able to see the triangle. Okay, and then to get to this intersection, there are 2 routes, and I'm going to give you an example. One route to the right, and then down, and that's one route, and the other route is down and then to the right. So there are 2 different ways to get to Fermat and Euclid. Okay, and then let's continue to go. So 1 plus 2 is 3, and then 2 plus 1 is 3. So I'm going to do one more explanation, and then I'm going to say, like, we're going to assume that the pattern continues. So for this street here, what are the 3 ways that we can get to here? Well, we can go all the way over and then down. That's one way. We can zigzag. That's the second way. Or we can go down and then all the way over, and that's the third way. Okay? So let's keep going. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Let's keep going. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Let's keep going. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. Now, I'm going to slow it down right now. So all of those were just from, like, all of these numbers are from the original Pascal's triangle. Here's the difference now. We no longer have a root here down to like a 1. So we're not adding this. So now it's almost like we're cutting off some of Pascal's triangle and just use what you have here. So don't take shortcuts. Don't use this formula every time. Like, don't count how many rows to the right and down and then plug it in. It's not going to work like that. You have to go through the steps. So 6 plus 15, I get 21. And I'm doing this with like a lighter color. I want to be able to see it. Okay. 15 plus 20, we get 35. 20 plus 15, we get 35. 15 plus 6, I get 21. 6 plus 1, I get 7. Okay, 21 and 35, I get 56. 35 and 35, I get 70. 35, 21, I get 56. And 21 and 7, I get 28. Okay, 56 and 70, I get 126. 70 and 56, again, I get 126. And then 56 and 28, I get 84. So 126 and 126 is 252. And then 126 and 84, I get 210. So finally, I get 462. So there are 462 roots to get from, let's just call it start to end, right? It could be A to B, start to end. Start to end. Example 2, counting the paths in an array. So how many different paths can we spell, Pascal, if you start at the top and proceed to the next row by moving diagonally left or right? So all this means is that, like, we're going to start with P. So there's one way to write P, and then we branch out. And there's one way to write PA, and there's one way to write PA. And then we branch out. And I'm going to put ones down the sides. Okay? At this point, I'm going to go 1 plus 1 gives me 2. So we can either go PAS this way or PAS this way. And then the 1 plus 2 is going to equal 3. So again, PASC, PASC, or PASC. So there's 3 different routes to get to this C value. And there's 3 different routes to get to this C value. And now this is when the Pascal's triangle changes, okay? Because we no longer have the triangle going out all the way. We have it tapering back in. So these are going to be different numbers. So 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then 4 plus 6 is 10. 6 plus 4 is 10. Now, if we don't taper back off to like one letter here, let's call it like letter, okay? What we have to do at the end is add these. So 10 plus 10 is 20. So therefore, there are 20 roots. Or 20 paths in this spelling of Pascal. All right, example 3, counting paths on a checkerboard. So assume that you can travel diagonally and upward. How many ways can the checker, so this is the checker with the circle, okay, reach the opposite side of the checkerboard? And then just note the X is a square that you cannot pass through. So we're used to flowing down, like from top to bottom. So now we're going to flow the other way. We're going to flow from the bottom to the top. So from here, we would go diagonally. So there's one path to get here and one path to get here. Please note, we can never reach this square or this one or this one because we're going diagonally upward. So diagonally left or right. Okay, let's go again. Okay, example 3, counting paths on a checkerboard. So assume that you can only travel diagonally and upward. How many ways can the checker, so this is the checker here, reach the opposite side of the checkerboard? So any of these white squares here. Okay. The x is a square that you cannot pass through. So that is the extension onto this question. Okay, so for the checker piece, we want to move up the board. Okay, so we've done all questions that we've moved down a triangle. So now we're going to go backwards. We're going to go up the triangle. So not backwards, upside down. Okay, so this checker can get here one way. This checker can get here one way. And we're never actually going to move backwards, so we're never going to be able to reach these squares. Now the checker can move this way one way and to this square one way. And again, we're never ever going to be able to go backwards, so we're never going to hit these squares. Now, the checker, if we do 1 plus 1 equals 2, there are two ways that the checker can get to this square. One way, two way. Okay, so let's keep going. The checker can get to this square one way. It'll never get to that square. And 1 plus 2 is 3. 2 plus 1 is 3. And we just branch off one way to here. Okay, the checker can get to this square one way, this square four ways, 1 plus 3. Now, we cannot go through this x, so this is basically a 0. We can get to this x square 0 number of ways. So we'll just leave that there. It's not 6. We can't land here. Okay, and then we have 3 plus 1, which is 4. Okay, we can get to this square. 1 plus 4 is 5. 4 plus 0 is 4. 4 plus 0 is 4. And then this just branches to the right. Just like how we would do the ones all the way down, since this square only has the number 4 like funneling into it, we would put a 4. Okay, so this square only has the 5 funneling into it, so we go 5. 5 plus 4 is 9. 4 plus 4 is 8. 4 plus 4 is 8. Okay, so we have 5 plus 9 plus 8 plus 8 different routes to get from one side of this checkerboard to the other. So I get 30. Therefore, 30 different routes to get from, let's go, to get to the opposite side.